Okay, so thank you for having me. I'm going to present this paper called Evolutionary Planning in Latent Space. And this is work done primarily by Thor and Dennis, and also together with Sebastian, who's also in the chat. So if there's particularly difficult questions, he might have to answer those. And we're all from the IT University of Copenhagen. Okay, so what's the motivation? Well, the motivation is that planning is a very powerful approach to reinforcement learning problems. So here we have a small industrial robot that needs to put these blocks in a certain order. And it can do that by thinking about the steps it's going to take in order to achieve that. But it requires a model of the world so that you can ask, what would happen if I do this? The robot needs to be able to imagine the outcomes of its actions and the effect it has on the environment. And that's called the world model. Unfortunately, such a world model is not available in many real-life problems. We simply cannot describe the world sufficiently well. And so in this paper, we propose to learn a world model that enables evolutionary planning in the latent space of the world model. And this can be seen as a kind of synthesis of two strands of research, one in world models and planning, most notably world models by David Ha and Jürgen Schmidhuber, and also the work by DeepMind in Go, chess, and Atari games. And then this other strand of evolutionary planning, where you try to use evolutionary methods for planning. So what does our approach look like? Well, this is a kind of busy slide, but I'll try to go over it step by step, and hopefully you'll get a better understanding. So the first step of our approach is to take the raw pixels from this reinforcement learning environment, this car racing problem, and encode that down into a smaller dimensional latent vector using a variational autoencoder. So here on the right, you can see some frames and how they look after being encoded and decoded. So you can see that the model kind of captures the high-level structure of the space. The second part of the world model is a recurrent dynamic model, which predicts future states, rewards, and whether the environment terminates, given the current state and actions. And this is the box highlighted in red here. Then the algorithm proceeds by, at each time step, evolutionary planning finds an optimal action sequence by evaluating it in the dynamics model. So it tries out this plan, this sequence of actions, using this latent dynamics model as a fitness function, basically, asking it what will happen in the environment if I do this. And then the evolutionary planning can find an optimal action sequence. And then it picks off the first action of that plan and executes it in the real environment. And if we just keep doing this, we can get something like this. I hope you can see the video. This is a car being controlled by this evolutionary planning, using this learned world model as an evaluation function. And you can see it does quite well in this environment. Yeah, so this is the main test case we track this method on. All right. So we have this is all nice and well, but we have a bit of a chicken and egg problem, because in order to train the world model, we need a policy, or we need rollouts. We need rollouts from the environment, and in order to get that, we need a policy. But in order to get the planning policy, we need to have the world model. So we bootstrap that by just using an initial random policy to generate rollouts from the environment, and then training the world model on that, and then using our planning policy using that trained world model. So that's what you can see here. You can see number of iterations on the x-axis. Iteration 0 corresponds to having this random policy that generates rollouts, then training the world model. and then using the planning policy, using that trained world model. And you can see that quite quickly, after a single iteration of this iterative training, we get quite high performance on this reinforcement learning problem. Yes. All right, that's it. And we also have a poster. It's a poster 157. And I tried to make a small visual memory aid here so that you can remember 157. So if you have a numpad, you need to make like a small triangle from 1 to 5 to 7. And you can look at this chessboard here. Your pawn, you want to strike the rook and check the king. Okay, hope to see you at the poster, and thank you.
Thank you a lot, Rasmus, for your presentation. And as you know, in these short presentations, we have no time for questions, but Rasmus and I believe his colleagues will be available at the poster section. So we are looking forward to that. So